Good afternoon. My name's John Pakes and I'll be taking you through Module 2 Physics for B1 engineers. During the next 50 minutes to 1 hour, we'll be revising Chapter 2 of Module 2, which is Mechanics. And hopefully over the next 50 minutes or so, we'll be able to cover the following areas. That is scalars and vectors, coplanar forces, and with that, moments, equilibrium of coplanar forces, stress and strain, simple machines, and friction. Now, before we get going, just some revision about mechanics in general. There's a definition here that I've put up on the slide, and it is that mechanics is an area of science concerned with the behaviour of physical bodies when subjected to forces or displacements and the subsequent effects of the bodies on their environment. Now, in this particular video, we'll be mainly concerned with a branch of mechanics known as statics. As previously said, we'll be dealing mainly with forces and how they act. So that brings us to another definition, and that is the definition of statics itself. Now, statics then are concerned with the equilibrium of bodies under the action of forces, and that in effect helps us solve problems which relate to statics in general. Now, the first part of this mechanics phase that we need to revise or look over are scalar and vector quantities. And the first thing that we will look at is the scalar itself. What is a scalar? Well, a scalar quantity then can be thought of as a quantity that has basically magnitude only. If we can see on the screen, we have what is in effect a scale or a temperature scale. It's one-dimensional in nature. Okay, that is the scale either goes up, as we can see, or it can retract and go in the opposite direction. Okay, the important thing to remember here is a scalar is a quantity that has magnitude only. Examples of scalars include, as you can see on the slide, speed, mass, energy, temperature, distance, etc., etc. Okay, these are all scalar quantities. They basically only have magnitude. That is some value. Okay. The next quantity that we need to revisit are vector quantities. Okay, what we can see on the screen here is a vector quantity. Now, vectors can be represented or expressed either algebraically, that is by a letter, and these letters can be printed in bold, or they can have arrows above them, or they can have lines below them. But in this case, upon what you can see is we can also represent scalars geometrically. And this is usually represented by means of an arrow. Now, what is a vector and what makes it different to a scalar is this arrow has both magnitude, that is, it has a length, and it also has a direction. Okay, so as I've said previously, the length of the arrow is its magnitude. In this case, it's given by the letter R, equivalent to 10 units. And its direction, in this case, is given by an angle. It may be an angle of rotation. Now, what examples are there of vector quantities? Well, by looking at the screen, we can see that velocity, acceleration, momentum, displacement, which is different to distance, force strength, force itself, and field strength. If we're looking at electric fields, they are all vector quantities. That is, they have both magnitude and direction, and it's important to be able to differentiate between the two. Okay, now if we want to represent our vector quantity specifically in some area of space, we have what is known as a space diagram. And what we can see from the screen here is this space diagram. It's the same vector as that was on the previous slide, but now we've put it somewhere, we've located it somewhere specifically in space. When dealing with space diagrams, we've normally always got some axis involved. And as you can see in the top left-hand part of the screen here, I put a small XY axis. And it gives you it gives the vector some relative dimension in space. Okay, so that is a space diagram. Now, when dealing with vectors, okay, you may deal with one or more vectors. You may want to know what is the resultant of these two vectors. Say, for instance, we had two forces acting on a body. You may not be interested in them individually, but you may want to know what is the overall force acting upon that body. Now, to answer this problem, we can use what are known as rules of vector algebra. And that's what we should be looking at now. There are different rules for different situations, but they should all really at the end of the day come up with the same answer if carried out correctly. And we're going to look at a few of these simple rules. The first rule that we're going to look at with respect to vector algebra is vector addition, and this is by a method known as the triangle method. Okay, so I have two vectors here. We have vector OA, so that is the length OA, and we have the vector B, or you could say AB in this case. Now, these vectors may be anywhere acting upon a body, but when we add them together, okay, we can find the resultant or the sum of the two vectors. And this resultant or sum of the two vectors is represented by the dashed line OB. And in this case, as it says, the line OB represents the resultant of the two forces. Now, what you do need to know here then is if we're adding vectors, say vector A plus vector B, the plus sign refers to the addition of the two vectors, and it should not be confused with just simple scalar addition, such as 8 plus 5. We're actually adding two geometric dimensions in space together. What is also good to know is the fact that the order that the vectors are added in, as long as they're added correctly, does not matter. In this case, what they've done here is they've added, on this next slide, is they've added vector B to vector A. At the end of the day, if it's done correctly, the resultant R should have the same direction and it should be of the same order of magnitude, that is, in the same length. Now what you can also notice is the way that the vectors are added together. The vectors are added together tip to tail, and the resultant should always be from the origin of the first vector going up to the head or the tip of the last vector that is being added together. Again, this is important to know when carrying out vector addition. Another rule that can be used in vector addition is known as the parallelogram rule. But before we get there, this slide is just showing you the fact that if we do not add the resultant or place the resultant from the origin to the tip and we place it in the other direction, we get what's known as an equilibrium. And this is basically saying that the vector sum, that is, if we add all the vectors up and we add the equilibrium up, they will cancel each other out, i.e. the vector sum or the sum of all the vectors will be 0. So just bear that in mind. As I said previously, another method for vector addition is known as the parallelogram method or the parallelogram rule. And the parallelogram works like this. If we've got two vectors, we've got vector OB and we've got vector OA. The sum of these two vectors is the vector OR. If I was to move the vector OA across to the blue dashed lines on the slide, well then you'd see that it would form basically the other length of a triangle. Okay, you can see by the dashed lines, which are representing basically the two vectors OA and OB, they form a parallelogram. And the diagonal between the two far sides of the parallelogram is the resultant. Not only will this give you the correct magnitude, it will also give you the correct direction when adding the two vectors up. Okay. Now, if we needed to add more than two vectors up, we just keep adding and adding until we come to our sum. And what we're in effect doing is we're forming a polygon. And as you can see on the slide, this form of vector addition is known as the polygon method. And we should briefly have a look at that. Okay, so what we have here is we've got three vectors. They are all acting from the same point, which makes the addition a lot simpler. And as the rule said previously, we can add them up in any order we want. We should still theoretically get the same resultant. But if we now take these three vectors, vectors A, B and C, and take them apart, keeping their direction and their magnitude as accurate as possible, and we add them up, we get what you now see on the next slide. We've taken vector A from the origin, we've added vector B to it, just adding it in its correct orientation in space. By adding those two vector A and B together, we get the sum of those two vectors, which is the dashed line A plus B, vector A plus B. But if we now add the third vector onto them, vector C, we now join up from the origin to the tip of the last vector, we now get the vector A plus B plus C, which is the resultant of all three vectors. And that is known as the as a polygon rule. Okay, if you have even more vectors, well, you go on and form a polygon with a greater number of sides, etc., etc. And you can see the dashed lines there that are forming up the vector sum of 2, 3, 4 vectors, and then finally are the resultant of 5 vectors. Now, if we have two vectors, say vectors A and vector B, and both vectors A and B are parallel to some x and y axis, therefore they're at right angles to each other, then the vectors A and B and the resultant, which we'll call C, form basically a right-angled triangle as such. So there we've got vector A and vector B acting parallel to the x and y axis shown up in the corner of the screen, and we now have some resultant, and they've called the resultant there R. It could have been C, and that resultant is basically the hypotenuse of a right-angled triangle. Therefore, it's possible in this occasion to use trigonometry to find the resultant of the following two vectors. That is, that these vectors are at right angles or perpendicular to each other. And from that we can also find the direction. Now the direction must be specified from some known axis, and this is usually from the positive x-axis as drawn above on the left-hand side of the screen. Okay, so by using trigonometry, this resultant can be found. The resultant's magnitude, okay, is found by using Pythagoras' theorem. That is the square of side A added to the square of side B, or the lengths of the vectors, the magnitude of the vectors A and B. Squaring them, summing them together, and then finding the square root will give you the value R. That is its magnitude or length. Okay, the direction, just quickly going back, the direction is found, the direction theta is found just by looking at the fact that that resultant is related to the tangent of the angle theta. And the tangent of the angle theta is equivalent to the length B divided by the length A. Now that would only give you the tangent of the angle, which is a ratio of two lengths. To find the angle itself, which is the direction of the vector R, the resultant R, you find the tan to the -1, or commonly known as the arctan of that angle. And that will give you the angle or direction. There is a simple example there on the screen to just reinforce that trigonometric method of solving two vectors that are at right angles to each other. And the example states, calculate the resultant of two forces, A and B, force B being equal to 3 newtons acting due north. Remember, these are vectors, so they have direction as well as magnitude. And force A equal to 4 newtons acting due east. Okay, the sort of thing to answer these sort of problems is to draw a rough sketch normally of the two vectors, and then use simple trigonometry to solve for the resultant. And this is what we've had here. Okay, what they've placed here, there should be normally a compass sign that you would put in there, because you have to ascertain what is due north. but they've taken due north to be vertical on the screen. So B is 3 newtons acting due north, and A is 4 newtons acting due east. They're not drawn to scale, as can be seen, but I'm sure that you get the idea. Using Pythagoras then, we said that the resultant, okay, is always going from the origin to the tip of the last vector. All we've done here is we've added the 2 vectors up, but they're at right angles. The resultant's going from the origin, which is the start of A, to the tip of B. That angle there, shown in red, theta, and that is the direction. And that would be the direction from some known axis. The resultant then is just using Pythagoras' theorem, is 3 squared plus 4 squared, all square rooted, which will give you 5. This is just in effect a 3, 4, 5 triangle. The angle, slightly more complicated because it's using trigonometry, is just the value, again, the angle theta with respect to the resultant there is just the inverse or arctan of the length 3 divided by 4, which in this effect gives you roughly 37 degrees. Okay. Just taking this a stage further, okay, when dealing with vectors, and we're normally, certainly in this module, representing vectors as forces, it may be necessary to only deal with a specific component of an overall force, or the overall vector in this case. Now, a mathematical method of determining these components is known as the resolution of forces or resolution of vectors. Basically what we're going to do is resolve one overall vector into a number of smaller vectors. Again, an example shown on the screen there. What we've got is we've got one overall vector represented in red by the letter F. Now this overall vector can be resolved into 2 components. We're only dealing in 2 dimensions here. This could also be broken up into 3 dimensions, but in this case we're just going to keep it to 2 dimensions. That being, we have a horizontal component that I've put F subscript of X, and we've got a vertical component, F subscript of Y. Okay, and we need to be able to resolve this larger component, F itself, into these smaller components. If we're trying to solve problems, we may only want to know one of the 2 components and not the overall force in this effect. Okay, and we can do this then by some simple trigonometry. Okay, so we've ascertained the horizontal component of F being F of X, or F subscript X, and the vertical component being F subscript Y. The magnitudes of these components, again it's just using simple trigonometry, is F of X is F multiplied by cosine theta, and F subscript of Y is F multiplied by sine of theta. If we quickly go back to the previous slide, if I was to bring the vertical component across to the dash blue line, you would see that that length is opposite the angle F makes with the horizontal component F subscript of X. Okay, and what that would tell us is that F of Y divided by F, which is in effect the hypotenuse of a right-angled triangle, is equivalent to the sine of this angle. Subsequently, or using the same principle, this line F of X is adjacent to this hypotenuse of this right-angled triangle F. And by simple trigonometry, F of X divided by f is equivalent to the cosine of that angle. So advancing the slide once more, just by some simple transposition of formula, we can determine the values f subscript of x and f subscript of y just by rearranging those formulas. And we end up with, as I've said previously, f subscript of x is equal to f cos theta and f subscript of y is equal to f sine theta. Okay. Again, just to reinforce that principle, we have a simple example. A force F of 40 newtons acts at an angle of 45 degrees to the positive x-axis. Remember, it's a vector, so it must have some direction. And it's asking you there to determine the magnitude of the x and y components of the force. Okay, so it wants to know just their values. We know that they're acting at 90 degrees to each other and they form a right-angled triangle, all in total. So it only really wants to know the magnitudes. That is the value of the individual components. Again, to do this, we just use simple trigonometry. Okay, I've set up an axis there. And there is my vector component, 40 degrees, and it's at 40 newtons at 40 degrees to the positive x-axis. Okay. Now, again, to solve this, it's a matter of simple trigonometry. The force F subscript of x is adjacent to the overall force F itself, and the vertical component F subscript of y would be vertical or opposite the angle there. Okay, so using simple trigonometry, F subscript of y divided by F is equal to sine 40 degrees, and f subscript of x divided by f is equal to cos 40 degrees. Rearranging, just like we did previously, you can evaluate the amounts or their magnitudes. And doing this on the slide, it just shows you what it is in full. The magnitude of f of x is equal to f cos theta, which is 40 multiplied by the cosine of 40 degrees, which will give you 31 newtons. And the magnitude of f subscript of y is f sine theta, which is equal to 40 multiplied the sine of 40 degrees, which is equal to 26 newtons. Okay, what I would say is don't be in a rush to say these two things don't add together. They won't. Okay. Just moving on a stage then. Okay, so we've covered some vector quantities. We've said what they are, how they can be added together, various methods depending upon the situation that they are in. Okay, we then said that we're more likely to look, certainly in this chapter, at vectors as being components of forces. Okay, we just now need to look at some other aspects when dealing with forces. The first thing we look at are coplanar forces. Basically, what is a coplanar force? Now, coplanar forces then, well, these are forces then whose line of action act in the same plane, and they are said to be coplanar. So you must think in all the previous examples I've shown, where we've set up an axis, as an x and y axis. You can think of about it looking at along a sheet of paper. Going in, we have length and we have width or breadth, but we don't have any thickness. Okay, so that are two planes basically. We've got horizontal and a vertical plane as in that effect. So with that in mind, we are interested when dealing with forces who are acting in just two planes. We are interested in aspects of movement, whether that be rotational or whether that will be translational. And that's what we're going to look at now. If I have a body, then looking at coplanar forces, there are two forms of equilibrium we must consider. And if I have a body here, and this body is represented by this circle, this blue circle, and I have two forces, both of equal magnitude, but acting in opposite directions, okay, probably you could possibly annotate one of these forces to give it a negative term, just to show it's acting in an opposite direction. But regardless of that for the minute, or disregarding that for the minute, they are both of equal magnitude, but they are a distance apart. But because they are in equal magnitude, and if these were the only two forces acting upon this body, they are said to be in translational equilibrium. That is, the object, or the body, the circle, will not move either to the right or to the left of the screen. If we take this a stage further then, if in addition then the forces are acting along a common line of action then the object is said to be also in rotational equilibrium. So there are two things that we need to consider when considering problems or forces, or problems dealing with forces that are acting in two dimensions. Are the forces in translational equilibrium? Are they moving about the page, up or down, left to right? And is there a possibility that the body is rotating about this two-dimensional axis? If they're doing neither, they are said to be in equilibrium, both rotational and translational. Taking this a stage further then, if they are both, all these forces are both, or three forces in this case, if they are in rotational and translational equilibrium then, and they are acting from a single point, the forces are said to be concurrent forces. Okay, so it's just something there to bear in mind. This enables us then to look at another aspect of the chapter when dealing with the general case of equilibrium of rigid bodies, when basically a number of forces are acting. When we're dealing with equilibrium cases of rigid bodies in which forces are acting, then we generally use the concept of torque or moments, and that's what we're going to have a look at now. So moments, or as we'll come to look at a bit later on, torque. First of all, a definition. What is a moment then? Okay, well, a moment is a turning force producing a turning effect. That is a brief textbook type definition. But what does this mean? If we have a look at the screen, and I have got here a diagram of a moment arm. And this moment arm, it could be that you're looking down in a plan view of a door. And this moment arm has a length or a distance from its pivot point, the pivot point O there, it's got a distance D to the end of the moment arm. So that blue line is representing a rigid body who's pivoting around the point O. Now, if we apply a force a force whose line of action is represented by the arrow, and this line of action acts perpendicular or 90 degrees to the moment arm, then what you set up there is you set up what's known as a moment of force. And this moment of force is acting about the point 0, okay, or the moment arm, and it's equivalent to the force or the perpendicular force multiplied by that perpendicular distance d from the pivot point or the axis of rotation. Now, examples of these moments or turning forces then could be, as we said already, opening a door. Okay, the door is hinged, you apply a force to open it, using a spanner if you're thinking about mechanics, okay, or an aircraft control, creating a moment where the aircraft is pivoting or rotating around its centre of gravity, and the force is acting upon the control. The aircraft itself can be thought of then as the moment arm. As I said there, mathematically, it's given the units, it's the moment m is equivalent to the perpendicular force times the perpendicular distance to that force, d. Or sometimes F multiplied by S if we're talking displacement. Now, the SI units, okay, of a moment is the Newton meter, and the imperial unit of a moment is the foot pounds force. Okay, what you mustn't get mixed up here, especially when we're talking about torque, is that this Newton meter has got the equivalence units of work, which is also a Newton meter or a joule. Okay, but the two are not the same thing, so just do bear that in mind. Now, a few examples, very simple examples, just using the formula or the relationship of the moment. Then we've got a moment arm here that is pivoted about the point zero, or O, and it has length OB equivalent to 4 meters. There is a perpendicular force acting on this moment arm of 20 newtons. And very simply, the moment of the force about 0 is equivalent to the force times distance, which is equivalent to 20 multiplied by 4, which will give you 80 Newton meters in this case. Okay. More slightly complicated problem here is, what about if the force is not acting perpendicular to the moment arm? Well, if it's not acting perpendicular to the moment arm, we have to use some basic trigonometry, because this is where we would need to resolve the force to deal with the components really that are acting perpendicular to this moment arm. So we've got this moment arm here, we'll call it PQ. It is a moment is being created about the point P, and we've got a force of 28 newtons that is at 30 degrees to the horizontal axis, and that is acting at position Q. The length of the moment arm between P and Q is 3 meters, and the question being asked here is to calculate the moment that is acting about point P. You could think about it another way. If this was a cantilever arm here of length 3 meters, and we had some tie holding that has a force 28 newtons, that is supporting that moment arm Okay, we could ask what is the force that is keeping that moment arm horizontal. But here they just want to know what is the moment acting about P. So there's a couple of ways that you can deal with this sort of problem. Okay, as I said previously, because the force acting on the arm is not at 90 degrees, we need to carry out some basic trigonometry. Now the basic trigonometry that we use is we're just going to resolve that force 28 newtons into two components. There's going to be a horizontal component, F sub x, and there's going to be a vertical component, F sub y. Okay, so we've said the force F needed to be resolved into two forces. We've previously looked at resolving forces. F sub x is the force multiplied by the cosine of the angle, which is 28 multiplied by the cosine 30 degrees, which will give you a force of 24.2 newtons, roughly. And we have the vertical force or component, F sub y, which is equivalent to 28 multiplied by sine 30, which gives you 14 newtons. The thing to understand here is, why did we resolve them? Because we were only interested with one component of this force. Because the force F sub x is acting horizontally, it's actually acting through, it's passing through the axis of rotation, or the pivot point P, and therefore it has no moment since it passes through P. So the only component of the force we are interested in is the vertical component, which is 14 newtons. And therefore the moment acting about P is just the moment arm, 3, multiplied by F sub y, which is 28 sine 30. And it gives you an equivalent moment of 42 Newton meters. Okay. Now a lot of the times, okay, if we're going to solve problems involving forces, we treat them as being in equilibrium. We're only interested in two dimensions, so we're interested in the equilibrium of coplanar forces. And there's a couple of things that we need to know when dealing with the equilibrium of coplanar forces. Okay, here we have a moment arm. Again, it's acting about point O. Okay, so we've got this moment arm that's represented by this red line. Now, depending on how I place forces on here, this arm could basically, because it's allowed to pivot about O, could rotate in our two dimensions in a clockwise direction, i.e. it has what we call a clockwise moment, or it can rotate in an anti-clockwise direction. In this case, it's got an anti-clockwise moment. Okay. Now, if this arm is in equilibrium, that is, it is not moving, then the force A multiplied by the distance to the center of the pivot point, so that will be the distance from force A back to point 0 or O, must be equal to the force acting in the clockwise direction multiplied by the distance from that force to the center of the pivot point acting about O. Okay then. Another thing that can help us with solving these engineering problems is some terminology. In engineering problems then concerning moments, and concerning in this case equilibrium of coplanar forces, the following terminology is usually used then, okay, which is the fulcrum, which is basically the point or the axis about which the rotation takes place, the moment arm or a moment arm, sometimes known as a lever arm. Okay, what is this? Well, this is the perpendicular distance from the line of action of the force, the direction of the arrows, the line of action, okay, to that fulcrum. So it's that distance, but it must be perpendicular. It's the perpendicular distance, sometimes known as the moment arm. Okay, the resulting moment. Well, the resulting moment is basically just the difference in magnitude between any moments acting anti-clockwise as opposed to those acting clockwise. Okay. And as I've previously said, for static equilibrium or problems involving equilibriums or moments of coplanar forces, the algebraic sum of these moments is 0. Okay. So that is good to know. Because the algebraic sum of the moments is 0 then, that means that we're in total equilibrium. We're not rotating about a pivot point, and if it should be a beam that appears to act in free space, we're not translating either up or down or from left to right. And that gives us two statements which is helpful in being able to solve these sorts of problems. That is, that the anti-clockwise moments is equivalent to the clockwise moments. Also, that the forces acting up must be equivalent to the forces acting down. And this is pretty much what we discussed previously when showing those two diagrams about the body being in translational equilibrium, forces up equals forces down, and rotational equilibrium, i.e. the moments acting anti-clockwise must be equivalent to the moments acting clockwise, otherwise the thing would rotate and solving any problems would be difficult. It is because we're in equilibrium that these sorts of problems are known as static problems. All I've got to show you here is a basic number of some simple slides. Just demonstrating the points I have just mentioned, or certainly just one of them. We've got a problem here. We have a moment arm acting about a fulcrum. It's almost like a seesaw or a lever. Okay, and we've got a force, and we've got this force of 50 newtons, and it's acting in an anti-clockwise direction, 3 meters from the center of the fulcrum B. And we have another force, 125 newtons, that is acting at a distance y meters from the center of the fulcrum B. You can notice that both of these forces are perpendicular to the moment arm. What the problem wants or requires is it wants to know what is length y. To solve this sort of problem, we use the fact that we are accepting that our moment arm or our lever is in equilibrium. That is, we're in rotational equilibrium and we're in translational equilibrium. So the thing is static. With that in mind, we can go ahead and solve the problem. And because the thing is in certainly rotational equilibrium, we can say that the sum of the anti-clockwise moments, because it is the sum that we're interested in, is equal to the sum of the clockwise moments. Just quickly going back to the previous slide, we can see that there is only one moment involved on either side here because there are only one force. But if there's more than one force, it is the sum of those moments, not just the forces individually, it's the sum of the moments that we're interested in. So ACWM is equal to CWM. On the anti-clockwise side, then there was one force of 50 newtons, and it was a distance 3 meters from the center of the fulcrum B. So that would give us a moment, or an anti-clockwise moment, of 3 times 50, which is 150 newton meters. On the clockwise side, then, we had a force of 125 newtons acting perpendicular at a distance y. So that would give us a clockwise moment of 125 y newton meters. We need to know what the value of y is, so it's just a matter of some simple transposition of formula. We divide through the anti-clockwise moment side by 125, and that gives us the value of y, which is 150 divided by 125, or 1.2 meters. The Newton units cancel each other out, so we're left with meters, which is what we wanted, as y was the length. So the force was acting a distance, the force of 125 newtons, so it was acting at a distance 1.2 meters from the center of the fulcrum B. Very simple. Going on then, a slightly more complicated problem then, and this is, here we've got the same sort of situation. We've got now, though, multiple forces acting at distances all perpendicular from our pivot point, which in this case has been given no letter, but is represented by the blue triangle here. So again, it's like a seesaw problem. Again, we have to accept that this problem, that in this situation, that the lever is static, it is in equilibrium. So our moments acting in one direction must be equivalent to the moments acting in the other. But remember, it is the sum. And what the problem wants you to know or find out or determine is what force must be applied to the beam at point D to the main equilibrium. To maintain equilibrium, sorry. So we've got D acting at the end there. We don't know what direction it's acting in. So we could, to solve this problem, we can assume it acts in any direction. When solved, the value of D, its magnitude will be the same regardless of the direction. The only thing that will change is it will either be positive or it be negative. If it's negative, it just means it was acting in the opposite direction. Okay, so how do we go about solving it? Well, what we want to do is we want to have a look at the arrows and in what direction they are acting. Okay, we then need to look at what the value of the forces are, what is their magnitude, and multiply those magnitudes by the distance that they are to the center of the fulcrum. In this case, we have got a force A of 500 newtons acting perpendicular at a distance 3 meters to the fulcrum, but it's acting in an anti-clockwise direction. We've got two other forces, force B, 250 newtons at 1 meter from the fulcrum, acting in clockwise direction. We've also got force C, which is 100 newtons, but this time it is acting at 2.5 plus 1 meter, so that's 3.5 meters to the center of the fulcrum. Okay, and we've got force D, whatever direction it is acting, it is still acting at a distance 2, 4, 5 meters from the center of the fulcrum. And what the problem does not want to know, just to reiterate, is what force must be applied to the beam at point D to maintain equilibrium. So we've got to make some assumptions. The first assumption is we're in equilibrium. The second assumption is we've got to add a direction to D. And if we change the slide over, we can say here, and it's saying, let's say force D acts in an anti-clockwise direction. We've already assumed, because we're in equilibrium, that ACWM is equal to CWM. And now then, what is CWM? Well, it's the sum of all the moments acting in an anti-clockwise direction. We have 500 newtons multiplied by 3, which was A, plus D multiplied by 5. Okay, that gives us, that should be 500 multiplied by 3 should be 1500 newtons. My apologies. Okay, plus 5D. So we have 1500 newtons plus 5D. And that would be Newton meters. And in the clockwise direction, we have got 250 multiplied by 1 plus 100 multiplied by 3.5. So we have 250 plus 350, okay, which is equal to 600 Newton meters. To solve this problem then, okay, we've got to assume that ACWM is equal to CWM, and that is 1500 newtons, okay, plus 5D is equal to 600. Okay, so D is just a matter of some transposition of formula. D is 600 minus, well, that should be 1500, which is 5D is equal then to negative 900 newtons, or shall I say minus 900, dividing through by 5 then. I'm just going to my dividing through by 5. We have 900 divided through by 5, and that gives us 180. But that's negative 180 newtons. Okay, what I would say is ignore this slide, as there's been a numerical error there. But that would be minus 180 newtons. And all it means is that we've assumed that D acts in an anti-clockwise direction when it must act in a clockwise direction for the equilibrium problem to hold. That is the beam to balance itself. Just going on then, okay, a quick mention of the fact that if we have two equal forces but they act in opposite directions and basically they have their lines of action parallel to each other, then you have what is known as a couple, or you have set up what is known as a couple. Okay, now what does this mean? Okay, so I've just got a diagram here on the slide. We have a moment arm acting from point 0, okay, and we have a force acting in one direction, okay, and that force is a distance x from the fulcrum or the turning point. And we have another force, force D, another force acting parallel but in the opposite direction. And one thing to understand here, that is to set up a couple, these forces must be equal but opposite in magnitude, direction. They're equal in magnitude but opposite in direction. Now this force is acting at a distance D from the first force. So it's acting at a distance D plus X from the fulcrum point. Now what we have here is the total moment of the forces about 0 then is F multiplied by d plus x minus Fx. Okay, as I've said previously, because one of the forces is acting in an opposite direction, it must be assigned a different sign, i.e. a negative, because it's acting in the opposite direction. So we end up with a sum here of force times d plus x minus f of x. If I just, or if you just expand the brackets, we end up with fd plus fx minus fx. And that just reduces to f times d. So what we can say then is that our couple really, regardless of where it is acting or what point it is acting, the moment of the couple is really only relying on the fact of the distance between the two forces, which are acting in opposite directions but are parallel to each other. Now, as far as a couple is concerned, okay, then, as I've already said, the moment is independent of the position of the fulcrum. The moment was only dependent upon the dimensions of the distance in between the two forces, acting parallel but in opposite directions. Okay, then. And this is just trying to push the point home here. Okay, if we've got two forces here and they are acting a distance d apart, and we have an assumed fulcrum, it does not matter where that fulcrum is, it could be on the other force, okay, the moment of the couple acting is only made up, or a product of, the force, the dimensions of the forces, okay, multiplied by the distance between them. Remember that both forces acting vertically upwards and downwards are equal in magnitude. So it's only really reliant upon their magnitude and the distance separated from them. Now, couples are interesting, certainly as far as we're concerned, as torque is a turning moment of a couple. Now, torque itself is measured in Newton meters, and a torque, generally represented by the Greek letter tau, is equivalent to force multiplied by the radius, or the radius of turn. So it's the perpendicular force multiplied by the radius of turn. Okay. Now, moments in couples are of interest to us then, as in moments, couples and turning forces can be applied to simple weight and balance calculations, which more of would be said during the Module 7 phase. I've come to a convenient point here, so I will leave it here for now. And if you've got any problems, just get in touch via the e-learning website and we will try to get back to you in time. Thank you.